Hey folks, hope everyone's doing okay. We're getting pretty darn close to being done with all of this, and once again, it's Unit 7. I'm going to keep condensing down some of the concepts and topics that we're going to be getting into and talking about. One of them that I wanted to proceed with was talk about Compton effect. So as of now in Unit 7, we have discussed one of the main pieces of evidence of the particle nature of light, and that is the photoelectric effect. Remember, in Unit 6, we talked about some of the different wave characteristics of light, and now we're focused more on particle nature. So we have the photoelectric effect. In addition to that, we talked about how the formation of X rays in the last lesson. And now we're going to proceed into what's called the Compton effect, which utilizes X-rays in order to show evidence of the particle nature of light as well. So this is another one of those pieces of evidence of particle nature. Arthur Compton was a physicist at Washington University in St. Louis. He won his Nobel Prize for showing that photons indeed have momentum, which we talked about in the last lesson, by bombarding carbon fibers with X rays. Okay, so basically, what he showed was and found was that the momentum change of the X rays is also equal to the momentum change of the electrons that were kicked off of that carbon film that he was using to study this. So let's look at this picture here, real quick, that I have. All right, so we have our incident photon, very high frequency in the X-ray region of the spectrum. We have our target electron. Now, for our simple purposes here, we're going to just imagine that these electrons are at rest. The incident photon has enough energy to where this resting state electron is going to be kicked off of here. What he was able to do was measure the reflected or whichever way the scattered photon went after the collision with these electrons. And what he found was that the wavelength of the scattered photon was different after the collision with the electron. So he was able to measure both the electron movement and the wavelength or frequency of the photon after it was scattered. Okay, what he found was, and he developed this equation, that the change in the wavelength, so delta lambda, all right, the change in the wavelength is equal to this little formula, h over m naught c, and this m naught is the rest mass of the electron, so this is 9.11 times 10 to the negative 31st, times c, which is the speed of light, and then times 1 minus cosine of theta. Okay, so what we're going to do is we're going to keep this really, really simple. We're going to keep the angle at which the incident photon comes in, and we're going to only scatter it either exactly 90 degrees or we're going to make it perfectly collide and bounce back at 180 degrees. So cosine of theta is either cosine of 90 or cosine of 180. Okay, now, if we look at this, if this is cosine of 90, obviously cosine of 90 is 0. So if this incident photon comes in and scatters at 90 degrees, the electron will not scatter at 90 degrees. It would shoot over here. But anyway, what he found was that the momentum change of the electron due to the collision is equal to the momentum change of the incident photon due to the collision. And not only that, that this was an elastic collision. Okay, so cosine of 0 means that this is only going to change by one of these, what's called a Compton wavelength, which I have that written down here below. Okay, if this is 180 degrees, 180 degrees cosine of that is negative 1. So if this photon comes in, hits, bounces back, then the wavelength is going to change by 2 of this number. So if you just plug this number into your calculator real quick and multiply it by 2, you will know what the change in wavelength of the photon is going to be. So you're going to have your wavelength incident and your wavelength of the scattered photon after the collision with this target electron. Okay, now, with all that being said, We're going to keep this really simple. So by us keeping it simple, it may throw our numbers off a little bit. Compton found that the change in wavelength of the photon could be solved by combining both conservation of momentum and conservation of energy equations. Okay, so we know how to solve for the energy of a photon. E equals h times frequency. Now, since these are usually going to be in wavelength, you're going to have to sub in for frequency. You're going to have to sub in c over lambda n for that. Okay, so it's hc over lambda. Sorry, got lost on that one for a second while I was talking through it. So that's the incident energy. Afterwards, the photon has energy again. But the electron also has energy, which this is going to be in the form of kinetic energy, so 1/2 mv squared. Or we can look at this as the incident photon has momentum. And remember, we solved for the equation for momentum of a photon. Momentum of an electron, so this is the particle of mass, so remember this is just mass times velocity. And you have your scattered photon. Now, one thing to keep in mind, solving for energies on this one's actually a little bit easier because energies don't care which way things are moving. Remember, they're scalars. Okay, so it's just E initial equals E final. So energy of the photon initial equals energy of the photon final plus energy of the recoiled electron final. When you are dealing with momentum, momentum is very direction specific. It's a vector. So remember when we did the problems last year with momentum where a ball was moving to the right and then bounces off and moving to the left, you have to understand that directions matter. So if you have, just giving you a heads up on this, if your incident photon is moving to the right, it is positive. If the photon bounces and moves to the left, you need to make sure you make that a negative momentum or else your equations won't work out right. Okay? So in the end on this, what we should be able to find is we can calculate the velocity of this electron by solving either conservation of momentum equations or conservation of energy equations. And we should get the same answer. Now, here's what I was going to talk to you about. You probably on some of them won't get the exact same answer. If the energy of the photon is actually a little bit lower, so in the low region of the X-rays, then the energy before and after should come out pretty close. Okay? The higher energy you get is going to cause this electron to move at near the speed of light. The closer you get to the speed of light, the more our equations are going to deviate from each other. That has nothing to do with the math that we are using. What it has to do with is the fact that we're not taking relativity into account. The closer something gets traveling to the speed of light, the more we're going to have to factor in relativity. Now, kinetic energy equation of 1/2 mv squared that we tend to use, that is an approximation equation. We are not going to sit there and go into the relativistic effects on this. So, as long as your answers come out very close on your energies, you should accept that as victory on these problems. Okay? All right, so if I ever say anything about Compton wavelengths, this H over MC, this is called a Compton wavelength. Once again, you can plug that into your calculator. I do believe it is on the next handout solved for you, so you can just double check, make sure your number's right on that. Okay? Once again, if the incident photon just continues moving at 0 degrees, obviously there's going to be no change because cosine of 0 is 1 and 1 minus 1 is 0, so there is no change, which basically means one thing. The photon missed the electron. It just kept on going. 90 degrees, you're going to have one Compton wavelength change, and 180 degree, you're going to have two of these. Okay, so that's going to be the change in the wavelength. All right, I'm going to try to I'll probably just do what I did on the last one, just write up a quick practice problem and put it online with your problem sets for you guys to have. So if you want to take it down and put it in your notes or whatever, you can. I would appreciate it if we kept to what I asked on the last one and used only handwritten notes instead of my copies of things. So, at least write it down, make sure you guys understand what's going on with it. Um, and you can use some of those things on the test that's going to be coming up. I'm still not exactly sure how many different topics we're going to hit after this. I know there's some of these things, in here. I'm skipping some of this stuff that I did last year that I usually do because this topic's not on the AP exam and we're starting to run out of time. And I want to spend at least a week and a half or so reviewing over old concepts for those of you taking the AP test. Okay, so anyway, I'm going to go ahead and shut this video down. And like I said, beginning, hope everyone's doing okay. Kind of missed you guys. Getting kind of boring doing this every day, but that's okay. That's the reality of it. So hang in there. We're almost finished. Okay.